Okay, guys, we are ready to start the chapter 23 homework. All right, so let's look at our first question here. In the July 2007 issue, Consumer Reports examined the calorie contents of two kinds of hot dogs. Researchers purchased several samples of different brands. Meat averaged 111.7 calories compared to 135.4 for the beef. A test of the null hypothesis that there's no difference in mean calorie content is a p-value of 0.124. Would a 95% confidence interval include 0? Okay, so if my p-value is 0.124, I would fail to reject the null hypothesis because this is not bigger than 0.05. So if I fail to reject, that means I can't claim there's no difference in the calorie content. So yes, the high p-value means we lack evidence of a difference. So 0 is possible inside our confidence interval. Study examined the fat content in grams for samples of beef and meat hot dogs. There we go, a little bit better. Now you can get to those buttons a little easier. Okay. A study examined the fat content in grams for samples of beef and meat hot dogs. The resulting 93% confidence interval is negative 4.4 to negative 3.3. So the endpoints of this confidence intervals are negative. Now, if this is beef minus meat, that means the meat has to be of a higher calorie content than the beef, because when I subtract it, I get a negative result, right? So the mean fat content is probably higher for meat hot dogs, because this is the mean fat. What does the fact that the confidence interval does not contain 0? That means that there is a true difference, right? If 0 is inside our interval, we can't conclude there's a true difference. So the difference in the samples is significant. If we use this confidence interval to test the hypothesis, what's the corresponding alpha value? Well, this is a 93% confidence. So if I do, let me get my annotation up here. If I do 1 minus 0.93, that's 0.07. Now remember, with the confidence interval, that's like a two-tailed test with the 0.93 in the middle. So the 0.07 is split on the outsides, so half of it. So that would be an alpha value of 0.0, whoops, not 0, because it's percentage, so I'm going to make it a percent, 3.5, because I'd have 0.035 when I split it, so half of that, and then, oh, I'm sorry, I shouldn't be splitting it. It's the whole 7%, because the alpha value, right, when we draw the picture, we split the alpha value. It's a 7%. Okay. It would be, just we'll move on. A 90% confidence interval for the difference in mean fat content for meat versus all beef hot dogs is this. Explain why you think each one of the following statements is true or false. If one eats a meat hot dog instead of a beef hot dog, there's a 90% chance they'll consume less fat. No, that's not a good interpretation of a confidence interval. The confidence interval is about differences in the means and does not indicate which, no. There's a, no, the confidence interval is about means, not about individual hot dogs. That's a true statement. %of meat hot dogs have between these, no. The confidence interval is about means, not about the individual hot dogs. One is 90% confidence that mean hot dogs average that many Alaskan. Okay. Meat hot dogs average 1.3 to 6.5. No, the meat is not more because that would be if we were positive. Nope, so it should be true. Okay, and then if one were to get more samples of both kind of hot dogs, 90% of the time the meat hot dogs would average that much less fat than the beef hot dogs. There we go. And then if one tested many samples, they'd expect about 90% of the resulting confidence intervals to include the true difference in mean fat content between the two kinds of hot dogs. That should be true. All right. The scores on a standardized test for 330 students in non-traditional math classes were compared to the scores of 269 students in traditional math classes. Computer software was used to create a confidence interval for the difference in the mean scores. Okay, here's our confidence interval. What is the margin of error for this confidence interval? So take a look at what we're doing here. Our confidence interval goes from 6.386 to 12.214. Smack dab in the middle should be the sample mean that we got. And this distance here is the margin of error, and this distance here is the margin of error. So if I subtract these two, it's twice the margin of error. So I'm going to go 12.214 minus 6.386, and I get, let's just do it on our calculator. I don't know why I'm giving myself trouble here. So we're going to go 12.214. 12.214 minus 6.386. But remember, that's twice the margin of error. So I've now got to take that result and divide by 2. So we get 2.914. If a 90% confidence interval is created, would the margin of error be larger or smaller? Okay, so again, let's look at our picture here. See, when I have a 98% confidence interval, that means that the 0.98 is in the middle and the rest is split on the outside. Well, if I've got a 90% confidence interval, notice that to have 90% in the middle, it would have to be smaller, right? This is the 0.90. So the margin of error would be smaller. So our margin of error would be smaller because the critical value decreases as the confidence level decreases, and the margin of error increases as the critical value. Oh, no, we're keeping the same sentence. And the margin of error decreases as the critical value decreases. They really worded that weird. Okay. Explain what the calculated interval means in this context. Let's clear that off. Alrighty, and let me get rid of that. All right. The scores on a standardized test for 330 students. Oh, I'm sorry. What am I doing? I'm explaining what the calculated interval means in this context. Okay. So this is our non-traditional minus traditional. So the non-traditional students have a mean that's higher because I don't have 0 inside the interval, right? So we would say with 98% confidence, students in non-traditional classes are expected to score between 6.386 points higher and 12.214 points higher on standardized tests than in traditional math courses. What's the difference between these students? This is saying students in general, and this is saying a particular student. So we don't want a particular student. Okay, so we should have our answer there. Does this result suggest that students who learn math with non-traditional methods will have slightly significant higher mean scores on standardized tests than those in traditional classes? So the interval is above 0. There is strong evidence to conclude the students who learn math with non-traditional methods will have higher mean scores than those in traditional classes. A new approach for teaching mathematics was introduced that engages students in group investigations and mathematical modeling. After field tests in 36 high schools over a 3-year period, researchers compared the performances the new approach students with those taught using a traditional curriculum. During the study, students in both classes that used the new approach and traditional took algebra tests that did not allow them to use calculators. The accompanying table shows the results. Are the mean scores of the two groups significantly different? All right. So this is our mean of the algebra test score for students in the class that used the new approach, and this is the traditional. So the same would be the null hypothesis. The new approach should be better would be the alternative. That looks good to me. Okay. What did we do wrong? The new mean algebra score oh, it just says, are the scores significantly different? We don't necessarily believe the new approach is better. So this should be a two-tailed does not equal. I'm sorry, I didn't read the whole thing well. Okay. Do you think the assumptions for inference are satisfied? 36 high school students. So probably the traditional curriculum is the same. The groups are independent. The sample sizes are large enough. Okay, here's our results. So this p-value, 0.0001. That looks good. State the conclusion. What was our output here? 29 versus 38.4. So notice that our t is negative. This means lower. So the traditional students did better. It's not that they will always perform better. They perform better on average. No. It's not the mean. They're not going to get the same mean. On average, students who learn in the new class method do significantly worse on algebra tests that do not allow them to use calculators than students that use traditional methods. That's correct. All right, do consumers spend more on a trip to store A or store B? Suppose researchers interested in this question collected a systematic sample from 82 store A customers and 80 store B customers by asking customers for their purchase amount as they left the stores. The data collected is summarized by the accompanying table. Suppose researchers decided to test the hypothesis that means are equal. The degrees of formula, okay, all right. So we're saying, okay, they're equal and does not equal should be our hypotheses. Okay, so now we need to plug in. So we're going to go stat, tests. This is a 2-sample t-test. All right, let's put in our statistics 1. Mean 1 is 42. The standard deviation is 21. And the n is 82. Mean 2 is 53. Standard deviation is 18. And the n is 80. And we have a does not equal hypothesis and calculate. All right, so our t is negative 1.624. What? Oh, they might have done it in a different order. Did I do it in the wrong order? No, wait, 82 and 8. It should have been 80. Oops. I just typed it wrong. So I missed this. This should have been 80. So just a mistyping on my part. Okay, there we go. Negative 3.58. Big difference there. Our p-value is right here. This means scientific notation to the, we're going to move the decimal 4 places. So we're going to have 0.0.0004. So that would round to 5 since we're rounding to. Oh, we're rounding to 3 decimal places. 1, 2, 3. So actually, I'll round to 0. Okay, all right. Just do it. Go with it. It's fine. We normally never say a p-value is equal to 0, so I don't like that it did that. You'd say the p-value is less than 0.01. State the conclusion. Okay, this is a small v, so we're rejecting the null hypothesis. There is sufficient evidence that the means are not equal. All right, the data below show the sugar content in grams of several brands of children's and adult cereal. We want a 95% confidence interval for children minus adults. All right, check your assumptions and conditions. We would assume that these are independent, randomly selected. There's certainly enough data values there. All that stuff you got to check. Okay, so now let's clear out list 1 and let's type in these data values. What does this come up in? And not going to help me. Let's just do it on the calculator. I'm going to pause the recording while I type this in because there's no reason for me to just have you guys watch me. All right, I have finished typing everything in. Now for the moment of truth, we'll see if I mistyped anything. So we're going to go stat, tests, And we're going to do our 2 sample T interval. So option A here. No, wait, sorry. Option 0 here. 2 sample. All right, so we want to input the data, list 1, list 2, and 95%, calculate. So we get 30 point, round to 2 decimals, 30.66. And 39.40. All right, let's try it, see if we made an error. Yay, I typed them all in right. All right, let's interpret the confidence interval. Based on the sample with 95%, the children's cereal had more grams by a boundary of 30.66 and an upper boundary of 39.4. Okay, a study examined whether the content of TV shows influenced the ability of viewers to recall brand names in the commercials. The researchers randomly assigned volunteers to watch one of 3 programs, each containing the same 9 commercials. The shows were either violent, sexual, or neutral. Afterwards, the subjects were asked to recall the brands of the advertised products. The results are summarized to the right. Okay. I test of hypotheses that there's no difference in ad memory between programs with sexual content and those with violent, with significance level of 0.05. Has a p-value of 0.085. Okay, so our null hypothesis all right, it didn't conjecture one was bigger than the other, so it should be a two-tailed does not equal. Since our p-value is greater than 0.05, we cannot reject the null hypothesis. Is there evidence that viewer memory for ads may differ between programs with sexual content and those with neutral content? This is the exact same question. I'm not sure I understand. Didn't we just answer that? All right, so find our T statistic. Okay, so we're going to go to stat, tests, 2 sample T test, and we're going to input our statistics. So mean 1. Okay, 2.0, no, wait, we're doing sexual first. 1.55. And that standard deviation of 1.97. And then the end there is 105. And we're doing sexual and neutral, right? Yeah, neutral. So neutral is 3.02. And the mean is 1.73. And the n is 105. It does not equal. Let's do it. So our t is negative 5.775. And our p-value is, okay, again, scientific notation. So since we're rounding 3 decimals, we would round that to 0 because I'm moving 8 decimal places. I don't like putting a 0 there, by the way. I said that before. State the conclusion. We would reject the null hypothesis. Okay, and then, all right. A study examined whether the content of TV shows influenced the ability of viewers to recall brand names in commercials. Researchers randomly assigned them. Afterwards, subjects were asked to recall the brands of advertised products. Results in the table. Is there a significant difference in viewers' ability to remember brands advertised in sexual versus neutral? So again, that's a two-tailed. We want the t-statistics, so here's our data table. So stat, tests, two-sample t-test. First mean, we're doing sexual and then neutral. 3.01, 2.02, and 99. And mean 2 is 4.18, 1.63, and 101. And so our t is negative 4.50. And our p-value. 3 decimal places, we're moving 5. So again, it's going to run to 0. State our conclusion. We're going to reject the null. There is sufficient evidence that a difference exists. And a 98% confidence interval. It was 0, right? 3.01, 2.02, I think those are the values we just worked with. But we want a 98% confidence interval. So negative 1.78. Negative 0.056. All right, what did we do wrong here? Let's see. Let's see my data again. It was sexual. Oh, sexual versus violent. I didn't change. So the sexual is fine. Sexual. Violent is 3.49. And standard deviation is 1.52. And the N is 108. So negative 1.067. And 0.107. All right, so the average number of brand names remembered, what? The amount by which the average number of brands remembered is higher for viewers of sexual shows than for viewers of violent shows in the interval. That's, I guess that's what they want there. That's very weird wording. All right. Suppose an experiment was done to gather data on the number of unpopped kernels in microwave popcorn. Half the students in a class took home a bag, put it in the freezer overnight, popped it the next day. Other half took the bag, left the kitchen counter overnight, and popped it the next day. Each group counted the number of unpopped kernels. All right. So this has to be the larger since they're both negative. Do women spend more time talking on the phone than men? A student collects data from students at our university and reports a 90% confidence interval for men versus women. Okay. 0 is inside my interval, right? We go from negative to positive. Since 0 is inside the interval, I cannot conclude that one's higher than the other. All right, guys, remember also, leave that page, to click these questions and get your credits for those, for the videos and the reading the textbook. I'll talk to you again soon.